So welcome to our third lecture, dealing with gas laws. Like we saw in the previous lecture, a balloon full of gas is actually not full of gas. Unlike when we had a water balloon where the actual volume of the balloon is completely filled with the liquid, in a gas, 99% of the volume of the balloon is actually empty. There isn't anything actually in there. The gas itself is actually only occupying a couple tenths of a percent of the volume. So if the gas is actually occupying that small portion of the volume, why is the balloon inflated? How does the gas keep the balloon expanded even though it's occupying only a tiny amount of the volume? Well, the way we're going to talk about the gas is we're going to use a simple model. We're going to look at a single particle that has some mass and is moving with some velocity. Now, for a real gas, we'd have to be talking about zillions and zillions of particles, but we're just going to look at one, because we're assuming the particles are moving independently of each other. And second, we're going to look at two of the walls. For a real gas, of course, we'd have to trap it completely, totally englobe it. But for our purposes, we're simply going to look at two of the walls that the particle is within. So the particle has some mass, it has some velocity, so it's moving. And what's going to happen? Well, eventually it's going to hit the wall. And what's going to happen when it hits the wall? Well, what it's going to do is it's going to bounce off and go back the other way. And we're further going to assume this is an elastic collision. That is, the particle neither gains nor loses energy when it hits the wall, so it still has the same speed, it's just moving in the opposite direction. And eventually, it'll get to the other wall and bounce off that wall. Go back to the first wall, bounce off, go back to the second, bounce off, etc., etc. And so we're going to see the gas particles simply ping-pong back and forth between the two walls. So what's going on? Well, we said the particle has momentum, and momentum is conserved. Originally, the particle had left-to-right momentum. After it hit the wall, it had right-to-left momentum. Well, where did the left-to-right momentum from the particle go? Well, it went into the wall. The wall had to absorb it. The particle pushed on the wall by hitting it. And in fact, that is how the gas exerts pressure on the wall. The particles of the gas move until they collide with the wall. And therefore, the pressure felt by the wall depends on the momentum of the particle. The harder the particle hits the wall, the more the pressure the wall will feel. But that's not the only component. The particle exerts pressure on the wall every time it hits the wall. So the more frequently that the particle hits the wall, the more pressure the wall will feel. And so the pressure of the wall depends on the momentum of the particle and the frequency with which it hits the wall. If we do something that changes either of those, we're going to change the amount of pressure the wall feels. So we have our particle, it's ping-ponging back and forth between the two walls. What would happen if we added more energy to the particle? Well, if we add more energy, the particle will speed up. It'll have more velocity, which means it'll have more momentum. It'll hit the wall harder. If the particle hits the wall harder, that means the wall will feel more pressure. And so we have the first of the gas laws. The pressure of the gas depends on its energy. Well, we can talk about the energy of a single particle, but we said a gas would automatically be zillions of particles. And so the question is, how do we talk about the energy of zillions of particles? We need some sort of ensemble quantity. And what we most frequently use to indicate how much energy something has is temperature. And so we have the pressure of the gas depends on its temperature. And that is the first of the gas laws. That is known as Ahmotand's law. The pressure of the gas depends on its temperature. So what other things might we change? Well, this time we're going to leave the particle alone. It's moving back and forth between the two walls with whatever velocity it has. But this time we're going to move the walls closer. So what's going to happen? Well, the momentum of the particle is the same, the velocity is the same, but now the walls aren't as far apart. It takes less time for the particle to go back and forth between the two walls. That means it's going to hit the wall more frequently. And we said every time the particle hits the wall feels pressure. So if the frequency goes up, again, the wall will feel more pressure. And so we have another gas law. Pressure depends on how far apart the walls are. Working in three quantities, moving the walls closer together changes the volume of the container. And so the pressure depends on the volume of the container. But moving the walls closer together makes the container smaller. But it makes the pressure go up. So the relationship between pressure and volume is a reciprocal relationship. The pressure depends on the reciprocal of the change in the volume. If the volume gets small, the pressure gets large. If the volume gets large, the pressure gets smaller. And that is Boyle's law. What else do we have to consider? Well, up until now, we've been assuming that the wall was rigid, and that regardless of how hard the particle hit the wall would just stand there and absorb it. Suppose we make the wall flexible, that is, movable. When the particle hits it, what's going to happen? Well, it's going to impart momentum to the wall, which means the wall will start to move. If we don't want the wall to move, we have to hold it in place. That is, we have to exert a pressure on the outside that is equal to the pressure of the gas on the inside if we want the wall to stay in place. And so the pressure has to be equal on the outside and the inside. What's going to happen now when we add some energy to the particle? It's going to have more momentum. It's going to hit the wall harder. It'll have more pressure, which means it'll start to shove the wall back. The pressure inside will be greater than the pressure outside. The wall will be pushed back. The next question is, will it be pushed back endlessly? And the answer is no. Yes, the particle is moving faster and has more momentum, but something else is changing when the wall gets pushed back. The further the wall gets pushed back, the longer it takes for the particle to get back after each trip. And so as the wall moves back, the frequency goes down. And what's going to happen? Well, what's going to happen is eventually the increased momentum of the particle will be canceled by the decrease in frequency. It'll hit the wall harder, but less often. The effect will be to produce the same pressure. So in this case, adding energy didn't change the pressure of the gas. It changed something else. It moved the walls. In other words, it changed the volume. And this case is known as Charles' law. The volume of a gas at constant pressure depends on its temperature, because raising the temperature, adding energy, caused the gas to expand. How about if we add a second particle to our container? What's going to happen now? Well, two particles are going to end up hitting the wall twice as often. That is, they're going to significantly raise the pressure. They're going to double it. And what's the effect going to be? Well, that means the pressure inside is going to be more than the pressure outside, so the wall will be pushed back. And it'll keep getting pushed back. And it'll get pushed back until the pressure inside and outside is equal again. Well, how far is it going to be pushed back? Well, obviously, it's going to have to be pushed back so that the particles hit the wall half as often as the one particle did originally. And how far is that? Well, that's obviously twice as far. The wall is going to have to be pushed back twice the distance so that the two particles each hit the wall half as often as they would have before. And the pressure inside and outside will again become equal. And that is known as Avogadro's principle. The volume occupied by a gas depends on how much gas you have. If you double the amount of gas, that occupies twice the volume. And so, we have the ABC of gas laws. Amotin's law says the pressure of the gas depends on its temperature. Boyle's law says the pressure of the gas depends on the reciprocal of the volume. Charles' law says the volume depends on its temperature. And Avogadro's principle says the volume depends on the amount of gas. The problem is that unfortunate relationship sign, the proportional sign. It simply says that if you raise the temperature, the pressure will go up. But how much? This is science. We don't care that it goes up. We want to know how much it goes up. We don't want a proportion sign. We want a mathematical expression, something like an equal sign. But we can't just stick an equal sign in there because pressure is not the same thing as temperature. And so we're going to have to include a constant. And so Amotin's law says the pressure of the gas is a constant times its temperature. For Boyle's law, the pressure is a constant times 1 over the volume. For Charles' law, the volume is another constant times temperature. And finally, Avogadro's principle says another constant times the amount of gas. The important thing to notice in our description of the gas is we haven't actually talked about the gas particle itself, other than to say it has mass and velocity. And that's the nice thing about the gas laws. It doesn't really matter what the particle is, that is, what the gas we're talking about is. All the gases behave the same way. They have the same set of rules. They follow the 4 laws we've seen so far. Which means to describe a gas, you only need to know 4 things. You need to know the pressure, the volume, the temperature, and the amount of gas. And once you know those 4 things, you know all you need to know about that gas. And that's where we'll take it up in our next lecture.